In this video, I am going to explain linear block quotes, linear block quotes concepts. First of all, consider this one is the channel encoder. The channel encoder adds extra bits, that means redundancy to the message bits. The encoded signal is then transmitted over the noisy channel. These are the input to the channel encoder is message bits. Output of the channel encoder is the encoded bits. Encoded bits. The channel encoder adds extra bits. Extra, that means redundant. Redundancy bits to the these redundancy bits are called as parity bits. Parity bits. Next. These redundancy bits are called as parity bits. That encoded bits is passing through that channel. These are this one is the channel. Channel plus some noise. These encoded bits. Encoded bits is passing through the channel and some noise is added. Output of the channel is the encoded bits with some noise. Encoded bits with some noise. Next, channel decoder. These encoded bits with noise is applied to channel decoder. Encoded bits with noise. These bits are applied to channel decoder. The channel decoder output is decoded bits. Decoded bits. What is the main function of channel decoder is identify the redundant bits and use them to detect and correct the errors in the message bits, if any. The main function of channel decoder is identify the parity bits. The channel decoder identifies the redundant bits and use them to detect and correct errors and correct the errors in the message bit, if any. The main function of channel encoder is add some extra redundancy bits or parity bits to the message bits. That encoder the output of the channel encoder is the encoded bits. That means combination of message bits and redundancy bits. Sometimes redundancy bits are also called as parity bits. This encoded information is passing through the channel. Some noise is added. After that, the output of the channel is encoded bits or information with noise. That encoded information with noise is applied to channel decoder. The main function of channel decoder is decode that encoded information, and also the channel decoder identify the redundancy bits. Whatever the redundancy bits which are added at the channel encoder side, the same redundancy bits are identified by the channel decoder and use them to detect and correct the errors in the message bits, if any. Therefore, linear block code is the type of error correcting code. Linear block code is a type of error correcting code. Why it is called as linear block codes? In the linear block codes, the parity bits and the message bits have a linear combination. In the linear block codes, the parity bits, that means redundancy bits. Sometimes these are also called as check bits. The parity bits and message bits have a linear combination. Linear combination. Later, I will explain what is meant by the linear combination of these parity bits and message bits. Suppose the channel encoder transforms message information into code words, encoded code words. These encoded code words are represented by X, capital X. Capital X is called as encoded code word. Suppose X1 and X2 are two encoded code words. X3 is equal to X1 exclusive or with X2 is also a valid code word. Is also a valid code word. X3 is obtained. X3 is obtained with X1 exclusive or with X2. That means linear combination of X1 with X2. Therefore, linear block codes are called as block codes are called as linear block codes. Some linear combination is there. X3 is the another code word is obtained by the linear combination of X1 and X2. That means X1 exclusive with X2. Next, theory related to linear block codes. Suppose information sequence is divided into message blocks. First point here is information sequence is divided into or segmented into message blocks. This one is a message block 1. Block 1. Message block 2. And so on. Each message block contains k information bits. K number of information bits. Here consider channel encoder, channel encoder input is the message bits, output of the channel encoder is the encoded bits. Here, each message block contains k number of information bits. That means the input to the channel encoder is a message vector that is represented by capital M. The output of the channel encoder is the encoded code word or code vector that is represented by capital X, where M is called as message vector, and X is called as, and capital X is called as encoded code word or code vector. Encoded code word. Okay. Two power k bit messages are applied to the channel encoder. At the input side, 2 power k bit message vectors are applied to the channel encoder. Two power k means here possible message vectors are possible message vectors. vectors are here. M is equal to message. M is equal to M0, M1, M2, and so on. M 2 power k minus 1, where k is called as a message number of message bits in the each and every message vector. Here M0, M1, and M2 power k minus 1 are the message vectors. Each message vector consists of k information bits. Each message vector consists of k information bits. These are the M. Therefore, M is equal to all possible message vectors are represented as M is M0, M1, M2, and so on. M 2 power k minus 1. Here M is equal to M1, M2 individual message bits, and so on. Mk. Let M at k is equal to 3. Let k is equal to 3. Possible message vectors are M is equal to M 2 power k. M 2 power k minus 1 value is M 2 cube 8. 2 cube minus 1, that means M 8 minus 1, M7. Therefore, the possible message vectors are M0, M1, M2, and so on up to M7. Each and every message vector having k information bits. That means M is equal to k is equal to 3 means generally M all are possible message vectors represented by capital M, M1, M2, and so on Mk. Therefore, k is equal to 3, M1, M2, M3, 3 bits. These are the M0 to M7, all possible message vectors which are applied to the channel encoder. Each and every message vector is represented by this form small m1, comma small m2, and so on Mk. Here k is equal to 3, M1, M2, M3. 2 power k messages are possible, message vectors. 2 power k range is from here 1, 2, 4. Here M0, 0, 0, 0, M1, 0, 0, 1, M2, 0, 1, 0, M3, 0, 1, 1, M4, 1, 0, 0, M5, 1, 0, 1, M6, 1, 1, 0, M7, 111. Add 3. M7 means add 4 plus 2 plus 6, 6 plus 1 is 7. That means 111. Like that. These are the 2 power k message vectors. 2 power k message vectors. So the message vectors is range from M0 to M2 power k minus 1. Okay. Coming to output of the channel encoder. This is the input side. This is the output of the channel encoder. Output of the channel encoder means 2 power k n bit. Here n. At the input side 2 power k bit message vectors. Here 2 power k n bit distinct code words. Distinct code words. Distinct code words 2 power k distinct 2 power k n bit distinct code words are generated by this channel encoder. The code word generated 2 power k n bit distance code words are generated at the output of the channel encoder. Next, possible encoded code words are encoded code words or code vectors. Code words are represented by x. Capital X is equal to x0, x1, and so on. X 2 power k minus 1. 2 power k minus 1. All these are the message vector. In case of here, message vector here, code words encoded code words. Here capital X is represented by capital X is equal to x0, all the x0, x1 up to x2 power k minus 1, all the n possible encoded code words. Each and every encoded code vector is represented by x is equal to x1, x2, and so on, xn. Where n is called as small n is the number of encoded bits, number of encoded bits in the encoded code word. Encoded code word. Okay, next one. Here, this one is the channel encoder. Channel encoder. K information bits are applied here. K information bits. The channel encoder is transform K information bits into n encoded bits. N encoded bits. Therefore, linear block code is represented by n digit code word, information bits, parity bits. The channel encoder is added some redundancy bits. That means parity bits to information bits. Length of the information bits is k here. K is the total number of information bits here. Parity bits is the n minus k. This is the linear block code is represented by linear block code is represented by n comma k, where n is called as the encoded digits or bits. K is called as information bits. Parity bits are represented by parity bits, which are also called as redundancy bits or check bits. That is represented by Q is equal to n minus k. Q is equal to n minus k. Here, the number of encoded bits is represented by n is equal to k information bits plus Q parity bits. Therefore, Q is equal to n minus k. These are the parity bits. Coming to systematic form of linear block codes. Systematic form of linear block codes. In systematic form, in systematic codes, the message bits appear at the beginning of each code word and followed by parity bits. That is the definition of the systematic codes. In systematic codes, the message bits appear at the beginning of each code word and followed by parity bits and followed by parity bits. Capital X is the encoded code word of length is in bits. Encoded code word or vector. Sometimes it is also called as vector. That is X is equal to, it is represented by X1, X2, X3 up to Xn. And M is the message vector. Message vector of length is K information bits. K information bits. That is M is represented by M1, M2 and so on MK. M1, small m1, small m2 and so on MK are the individual message bits. Individual message bits of that message vector or message word, code word or message data code word. And C is the parity check vector. Parity vector or parity vector. Parity vector of length. Length is Q bits. Where Q is equal to n minus k. Q is equal to n minus k. Therefore, C is represented by C1, C2 up to CQ. Here, X is equal to X1, X2, and so on, and X3, and so on, X1, Xn. It is also represented by X1, X2, not X1, X2, here. M1, M2, M3, and so on, MK, C1, C2. This is the code word, encoded code word of length and bits in systematic form of that linear block codes. First message bits are appeared and then parity bits. These are the message bits are message bits and parity bits. In the systematic form of linear block codes, the first k bits are the first k bits, k message bits, q parity bits. The first k bits are message bits or data bits, and the last q is equal to n minus k, and the last n minus k bits are the parity check bits. Parity check bits. Okay. Now, first here message vector is represented by here x1 is equal to m1, x2 is equal to m2, x3 is equal to m3, up to xk is equal to mk. From this expression, x1 is equal to m1, x2 is equal to m2, x3 is equal to m3, and so on. Xk is equal to mk. This is the encoded code word or code vector, consists of n bits, x1, x2, x3, and so on xn. First bits are the message bits and the last bits are the parity check bits. The first bits means up to x1, x2, x3 up to xk are the message bits, m1, m2, m3, mk. That means x1 is equal to m1, x2 is equal to m2, x3 is equal to m3, and so on, xk is equal to mk. These are the first bits of the encoded code word. The first bits of the encoded code words are x1, x2, x3, and so on, xk are the message bits. That means x1 is equal to m1, x2 is equal to m2, x3 is equal to m3, and so on, mk. The last bits n minus k, and the last n minus k bits are the parity check bits. That means C1 is equal to here xk plus 1. The parity check bits formed in the linear combination of the parity check bits. The parity check bits formed is the parity check bits are formed in the linear combination of message bits. In the linear combination of message bits. Okay, C1, C2, and so on. CQ are the parity bits. These are the xk plus 1, k plus 2, and so on, xn. Linear combination of the parity check bits are formed in the linear combination of message bits. Suppose here message bits means here some parity coefficients are added here. P11, M1 exclusive are with P21, M2 exclusive are with, and so on. P K1 MK. That means here M1, M2, M3 are the message bits. C1 is the check bits. How C1 check bits are formed? C1 check bits are formed by the linear combination of these message bits. That means M1, P11, M1 exclusive are with P21, M2 exclusive are with PK1, MK. Linear combination. And C2 is also another parity check bit, is formed by P12, M1, P22, M2, and PK2, MK. And finally, last one. Here, P1Q. Here, Q is called as a number of parity bits. Q, P1Q, M1 exclusive are with P2Q, M2 exclusive are with here MK, MK, PKQ. Here n is equal to, here n is equal to k plus q, k plus. Therefore, the coefficient value is k. Here k plus q means here we use kq. Here C1, the parity bit value is represented by q. Here q, here q, P11, M1 exclusive are with P21, M2 exclusive are with PK1, MK. These are the P11, P21, PK1, all are the coefficients. Okay. Convert this into consider this one. Consider this one. Convert this into C vector, parity check vector here. C1, comma, C2, comma, and so on. CQ is equal to M1, comma, M2 and MK into some matrix. Matrix of the order is K cross Q. Here P11, P21 and so on, PK1 and P12, P22 and so on, PK2. Last one is PK1, MK, PK2, MK. Not here, MK is not required because and PKQ. Last one is here P1Q, P2Q, and PKQ. This is the C vector. C is equal to M vector and P vector. The dimensions of that C is 1 cross Q. The dimensions of M is 1 cross K. The dimensions of that P is K cross. Here 1 cross K. Here 1 cross. Here 1 cross K. K cross Q. See that where C is called as a parity check bit vector, M is called as message vector, P is called as some quotients are there, parity matrix. P is called as parity matrix. P is called as C is called as a check bit vector, parity check bit vector, parity check bit vector. M is called as a message vector. P is called as parity matrix, parity submatrix. This is the one important relation. Parity bits are determined by using this relation. Another important one is consider all these. That means convert these expressions into in another form, second form here. Second form is x1, x2, and so on, xn. That is equal to and so on. C1 message bits are M1, M2, and MK. Into here into 1 0 0 0 like that, 0 1 0, and so on, 0 0 1, and this parity vectors P11, P21, P11, P21, PK1, and P12, P22, PK2, P12, P12, here 21, here 21, P22, and PK2, PK2, P1Q, P2Q here, and so on, P1Q, P2Q, last one, so on, PKQ. Here, K cross Q. X1, X2, XN are called the encoded code vector bits. This is the X1, X2, and so on. XN are called the individual encoded bits. M1, M2, and so on. MK are called as the message bits. This message bits are multiplied with this entire matrix. We will get this information. Total x1 is equal to m1, x2 is equal to m2, x3 is equal to m3, xk is equal to mk, c1, c2, and cq. From this we have to design another equation, that is x is equal to m into g. Here, this is the identity matrix Ik and the P matrix P KQ. The total is called as that is the totally generator matrix. The combination is called as the generator matrix G. Generator matrix of order is K cross N. Okay. Now X is equal to 1 cross N, and the message vector is represented by 1 cross K, and the generator vector is represented by K cross N. These are the two important equations. First one is C is equal to MP, and the second one is X is equal to mg. Next, generator matrix. Generator matrix. It is represented by capital G. Dimensions of that generator matrix is K cross N. That means K rows and N columns. K rows and N columns. These rows of the generator matrix are the code words of the encoded code words of the linear block codes. Important, very, very important points are the rows of the generator matrix. The rows of the generator matrix are the encoded code words. Encoded code words of the linear block codes. Linear block codes.